So now we shall consider vibrations of a crystal. So as we discussed before, each degree of freedom of a crystal is specified by three components. L is the lattice vector of the unit cell. S is the atom inside that unit cell, the basis, and alpha corresponds to three directions of the Cartesian system. And the consideration we have given for the vibrations before was rather general. It applies to any type of systems. So, given the dynamical matrix D of our crystal, we'll have to solve this eigenvector eigenvalue problem to determine vibrations of a crystal. And because in this case the matrix D is of infinite dimension, because we basically have it's a matrix of two indices I and J, and we have an infinite periodic crystal. The vector Y of displacements is also an infinite vector. We have to set up this equation like that, and of course it's very difficult to solve because of its dimension. So what we do, we introduce Born-Kármán boundary conditions, in which we state that displacements of atoms um, are repeated along a very large um, um, periodicity of n1 unit cells along the direction of the vector a1, translational vector a1, n2 along the vector a2, and 3 along the vector a3. So we basically um, introduce a very large portion of this infinite crystal, um, which is n1 unit cells in the direction of a1, n2 in direction a2, and n3 in direction a3, and then we periodically repeat this big box. This big box is called main region of the crystal, and these are the conditions we set up for the displacements. So with this kind of periodicities, you have identical displacements in different boxes. For a one-dimensional system, this simply would mean that we have a Tor like this, and these conditions can be concisely written by introducing reciprocal space. So we introduce reciprocal basis vector B, which are related to direct basis vector A by this relationship. So this is a primitive reciprocal basis vector B. And then we introduce a Brillouin zone, um, in which we shall consider vectors K inside the first Brillouin zone. And then it appears that the solutions of these equations can be easily found if we assume that these displacements are proportional to these plane wave factors. So in order to see this, what we do, we multiply both sides of these equations by this kind of factor. So you see, these equations are written for a given L vector. We sum up over L prime. So we are free to multiply by this each side of the equation. So in the right hand side, we will have the sum of these YL displacements. I ignore the indices S alpha here. In the left hand side, we have something like that. But because the dynamical matrix depends only on the difference of the vectors L and L prime, remember we discussed that before, and this is the consequence of the periodicity of the crystal. We can replace the L summation here in this double sum by introducing a new vector L double prime, which is the difference L and L prime, and then replace the L summation with the L double prime summation. The thing is that we sum over all infinite crystal, and it doesn't really matter whether we displace this crystal by some vector or not. It's still the same crystal. But if we do this, and we make this change of variables, you will find that in the left-hand side, that double sum factorizes. So you have a separate sum over the L double prime vectors and a separate sum over L prime vectors. And that expression here is precisely of the same form as given here. This will be a vector, of course. But the vector, because we sum up over L prime, that vector would only be of the dimension associated with the S alpha indices, these ones. So in other words, it will correspond to the number of degrees of freedom within a the primitive unit cell of our choice. So this is a small number, finite number. If you have one atom in the unit cell, this will be just 3. If you have 2 atoms in unit cell, this will be 6, and so on. So this vector here, it has a dimension of S alpha. There is no L anymore. And this vector is the same. What about this one? In this case, we sum over the vectors L double prime. So this L double prime replaces this L minus L prime. And therefore, this expression here would be a square matrix also associated with these indices S alpha. So, as I said before, in the case of a system with a single atom in the primitive cell, this will be a 3 by 3 matrix. If you have 2 atoms in the unit cell, this will be a 6 by 6 matrix, and so on. So we can replace this matrix by a matrix D, and it has only these 2 indices, and this vector by the vector Y also with respect to these 2 indices. Of course, because of this vector K of the brilliant zone, this matrix and these vectors would have it as a label. So we shall obtain, by solving this problem, which is nothing but the eigenvector problem for each vector k, we shall obtain all the vibrations of this system. So the bottom line here is that initially we have a system of infinite dimension. But using the fact that the dynamical matrix depends only on the difference of the lattice vectors, not on each lattice vector separately, it was possible to represent this problem as a set of much smaller problems, still the infinite set, because each set corresponds to a typical vector k, and we have many vectors k in the first brilliant zone. Still, for each vector k, we have this finite size problem to solve to determine all frequencies for each vector k. So this way, we shall obtain all the vibrations of a crystal as a function of the vector k in the brilliant zone. So these eigenvectors would give us how atoms displace. Remember the case of the linear or water molecule, where we saw how actually atoms move for each particular normal mode. And this omega square would give us for each normal mode a corresponding frequency. So if we have, say, one atom in the unit cell, this would be a 3 by 3 problem. So this will give rise to 3 normal modes for each vector k. If we have 2 atoms in the unit cell, we have 6 degrees of freedom in the primitive cell, and this will give us 6 frequencies and correspondingly 6 normal modes. Once we know these eigenvectors, we can actually calculate the actual displacements by converting this expression. And the matrix dk for each vector k is obtained as this lattice sum. And because the dynamical matrix decays with the L, so remember the dynamical matrix corresponds to the second derivative of the total energy with respect to atomic positions. There are some mass prefactors, but these are irrelevant for this. And therefore, it would relate to interaction between atoms of different cells as we sum over L. And these interactions, of course, decay as we move away one atom from another. Therefore, this sum, in this sum, we would need to retain a certain number of vectors L around the zero vector. So this sum can be actually calculated.